Previously, we had defined chemistry as being the scientific study of matter, the properties of that matter, and the transformations of that matter. So it's important at this point that we start talking about how we take a scientific approach to solving problems. And that's going to be a key sort of concept throughout this class, is using a scientific approach to investigate different phenomena. So we define chemistry as the scientific study of matter, its properties, and its transformations. So a useful question to ask is, what do we mean by science? So if you want to know what a word means, a good way of doing this is to just Google and look at the Wikipedia article, or if you want to be old school, you can look in the dictionary. So that's what I did. I looked up the word science in the dictionary. I used an American dictionary, the Merriam-Webster dictionary. And in that dictionary, they define science as being knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through the scientific method. So there are sort of some words in there that we need to unpack a little bit. We may not know what is meant by a general law, and we also may not know what is meant by it through scientific method. So this is a little bit kind of complex, this definition, so I came up with my own simpler definition. And I'm going to tell you that science can be simply defined as an approach to the study of problems. Right? It's a way of tackling problems. But we're going to begin with an assumption in science. And the assumption that we're going to begin with is that the universe, everything around us, obeys laws of natural origin. Now, this is interesting. So what do we mean by laws? We mean rules. And what do we mean by of natural origin? We mean that they are not made by us. They're not made by people. They just kind of exist. They are natural. They're just there. Now, the thing about these laws of natural origin is that they are unchanging. So if I make a societal law, that is not a law of natural origin. That's a law that is made by us. The other thing about societal laws is that you can change them. If you don't like them, you can, vote out your congressman and get rid of the law. You can appeal the law. There's a whole sequence of processes that you can go through to get that law overturned or modified, right? So these laws that we're talking about, they're just kind of there, and we can't do anything about them. We can't change them. We can't make them any different. And what we're trying to do in science, what we as scientists are trying to do, is to identify and understand these laws of natural origin. And the tool that we're going to use for doing that is called the scientific method. So we want to identify what are the rules that the universe operates by, and how do those rules operate. Yeah? Okay, so that's basically what's going on. So what is this thing called the scientific method that we're going to use to identify and then explore how these laws operate? Well, the scientific method is a generalized procedure. That means that, it's not a step-by-step protocol that is used every single time we encounter a problem. It's a concept in the back of our minds that we're following through with, right? So this generalized procedure is used to obtain new information and explain what we call natural phenomena. And we should distinguish that from supernatural phenomena. Natural phenomena are things that we can observe. Okay, we can definitively observe them. So within the scientific method, we always have the following sort of key steps. The beginning of the scientific method, we identify the problem and we make plans to collect information, or what we call data, about the problem. Then we collect data about the problem. And there's two ways of doing this. One is through observations. You just look at it and you make notes. And the other is through experiments, where you systematically, test things and modify things and see how your system responds. Now, once you've got a bunch of data, what you're going to do with that data is you're going to analyze that data and you're going to try and get some generalizations about that data. You're going to try and summarize what you have observed. So this is kind of, at this point, you don't know why things are doing what they're doing. You just know what is happening. You've just got a bunch of data and you've kind of tried to summarize it in some way. The next step is where things get really kind of fun and creative. What you do now is you try to explain why you are observing what you are seeing, right? You come up with, ideas for why things are doing what they're doing. And then finally, what you have to do is test if your idea is correct or incorrect, right? So you're going to do some more experiments, make some more observations, and see if your potential explanation is correct. So it kind of looks like this in a flowchart, right? You make observations, you perform experiments. And if you're doing this well, it's always good to know the conditions under which the observations are made, right? So if you were observing a patient's heart rate, you would want to know whether they were at rest or whether it was after exercising. That's a good example of that, right? Okay. Now, once you get, sort of a large collection of observations, you can summarize them. You summarize them in what is called a scientific law. And a scientific law, sometimes it's just like a statement of fact. So a good example would be something like, what goes up must come down. That's a scientific law describing Newton's law of gravitation. Okay, so that would be sort of as a sentence, as a sort of, a statement. But it can also be written, a scientific law could be written as a formula. So we might have like F equals ma. That's a formula. It doesn't tell you why things do what they do. It just tells you what things do. So once you've so the end point from your observations, the best that you can get from that at that point would be like a summary called a scientific law. What you're going to try and do next is to explain why you are seeing what you are seeing. What's the reason for what you are seeing? We call this forming a hypothesis. Now, a hypothesis is a testable explanation, and it's important to recognize that in science, any of our hypotheses that we propose, they have to be testable. So you can't come up with a hypothesis that it's not possible to check to see whether it's correct or not. And this is different from hypotheses in other disciplines, perhaps like mathematics or philosophy, where they often don't have that testable characteristic. Okay, so all scientific hypotheses can be tested. If it can't be tested, it's not science. So once you've got your tentative explanation that we call a hypothesis, what do you got to do next? Well, you got to test it, right? So you're going to collect more data, you're going to perform more experiments, you're going to do more observations and see if they are consistent with your hypothesis. If they're not consistent with your hypothesis, then you're going to revise your hypothesis. Now, when we do these experiments, when we make these observations, we try and measure only one thing at a time while keeping everything else constant. We have what we call well-controlled experiments. Now, this can be sometimes, a little bit difficult, right? Particularly when you're dealing with natural systems like people or something that's very large, like an entire planet. So if you're studying the climate, it's hard to study rainfall in the absence of something like wind. You can't say, okay, wind, stop blowing, I want to measure rainfall. It's not going to happen, right? So this is kind of like an idealized thing. And the same thing with like people, there's multiple things going on at once and it's difficult to control everything, but we try our best to limit that what is changing to one variable. Now, once we've got a strong, well-tested hypothesis, and then what happens is the hypothesis kind of gets promoted in status and it gets promoted to what we call a theory or a model. So this is kind of like an arbitrary sort of distinction. Once your hypothesis has been what we call well tested and is generally accepted by the scientific community, it gets promoted to being the status of a theory, right? And the cool thing about theories is that they can explain the results of a very large number of experiments, and they can also predict what is going to happen in cases that we have yet to observe, right? So we can make predictions using these models or theories. Now, it's often said that a good theory avoids complexity. So the famous Einstein quote is, you don't really understand something unless you can explain it to your grandmother. So good theories are often simple and elegant. We're trying to avoid unnecessary complexity in our theories. And then, of course, once we've got our model or theory, we're going to continue to test it. And if we do find any data that disagrees with our model or our theory, we're going to revise our theory and we're going to continue to improve it. And it's going to get stronger and stronger and better and better. At least that is what we hope. So it's also useful to talk about what we mean by the term a scientific fact. So a scientific fact is a reproducible piece of data obtained through an experiment or perhaps through an observation, right? So an experiment is something that we create to observe natural phenomena, and an observation is just kind of like looking at the natural world and seeing what's going on. Now, what scientists do with all of these facts that they collect is that they publish them, right? And they publish them in what we call peer-reviewed journals, where other scientists have double-checked that the experiments were conducted in an appropriate manner, in the best way that we currently know how to do. And then other scientists will look at those published results and they'll critique them and they'll double-check them, and they'll confirm that these things are valid scientific facts. You can see these are all a bunch of chemistry related journals, and you can see that chemistry covers a huge sort of like range. At the top here I've got a bunch of journals that are primarily concerned with obesity and diabetes, and in particular pediatric diabetes and pediatric obesity. And then at the bottom, we've got a whole bunch of stuff that's concerned with like materials, right? And so chemistry is going to cover all of that. So from medical science all the way through to some very, very practical applications with respect to materials. Now, you're going to collect a bunch of scientific facts through making observations and performing experiments. And when we have a whole big collection of scientific facts, what do we try and do with them? We try to explain how those facts are related to one another. And this is where that concept of a scientific law comes in. And what a scientific law does is it summarizes facts, but it doesn't explain why a phenomenon occurs. And as I mentioned previously, a scientific law can be either a statement in words or it can be a mathematical formula. So Newton's law of gravitation, what goes up must come down, or alternatively as a formula, F equals G m1 m2 on d squared, right? Both of those are scientific laws. They tell you what happens, but they don't tell you why. I also mentioned previously that scientific laws, unlike societal laws, they're not arbitrary. They're not just invented by people. They are things that exist with or without us knowing about them. And also, scientific laws can't be changed, unlike societal laws. Okay, so scientific laws are formulated right at the beginning of the scientific method. Once we have a collection of observations, we've perhaps summarized them in terms of a scientific law. What comes next is we generate what's referred to as a scientific hypothesis. And a scientific hypothesis is a testable explanation of a series of observations or a scientific law. So The characteristic of a hypothesis is that it is a plausible but tentative explanation, and it has to be able to be tested. So if somebody was to come into a clinic and they were sweating and they looked flushed, right? A plausible but tentative explanation could be that they have a bacterial infection that is giving them a fever, and I could test that. Another plausible but tentative explanation could be that they had just been running, okay, and therefore they are hot and sweaty. And I could test that as well by asking them, have you been running, right? Okay, so that's kind of like an example of a plausible but tentative explanation that could be tested, all right? Now, we can conduct experiments to disprove a hypothesis, but we can't ever definitively prove a hypothesis. We can eliminate a hypothesis as not being a possibility, but we can't ever 100% prove a hypothesis. It's always a little bit kind of open to potentially being wrong, because at any point in time, someone could come along and think of a better experiment or a more elaborate example that we never thought of when we were formulating our hypothesis, and suddenly our hypothesis is not correct. It should be pointed out that there are definitions of a hypothesis from non-scientific disciplines that are often slightly different, and generally how they're different is that they omit the testability requirement. Non-scientific hypotheses are often found in philosophy and in mathematics. So in this example, what we're going to do here is we're going to classify each of the following statements as either a scientific fact, so that's a piece of reproducible data, a scientific law, a summary for more than one observation or experiment, a summary of the results of more than one observation or experiment, or a scientific hypothesis, which is a tentative explanation that is testable. So here we go. It says in statement A, in an experiment, so it's a single experiment, a log was observed to burn with an orange flame. Well, that's going to be a fact. Okay, fact. There we go. It's going to be a fact, right? It's just one experiment. It's reproducible. We could do this again and again and again. A log will burn with an orange flame. It's just the result from a single experiment. We call it a scientific fact. So then in the second statement, it says burning logs, so it's more than one observation or experiment, generate heat and light. Okay, so that's a bunch of observations as a result of the reaction between cellulose and oxygen. And the key thing here is this little bit in here. It says as a result. So what that's telling me is I'm explaining why we get heat and light, right? I'm saying it's because of the reaction between cellulose and oxygen. So what this is a scientific hypothesis. And I could test it by doing the experiment in an oxygen-free environment, and I could show that oxygen was necessary for this reaction, right? And then perhaps I could identify the presence of cellulose, and I could continue to test this hypothesis. But that hypothesis, it would be possible to test it. In the third statement, it says burning logs generate heat and light. It's multiple logs. So it's not a scientific fact, it's multiple things. It's not telling me why they generate heat and light, it's just saying that they do, right? So it's a summary of more than one experiment, more than one observation. So this must be a law. Okay. In the final statement here, it says a burning log. So it's a single experiment, a single observation. A burning log was observed to generate heat. Doesn't tell me why. It's just a single observation, so therefore that is classified as a fact. Okay. As I mentioned, when a scientific hypothesis has been tested and validated over a long period of time, sometimes like years or decades or even centuries, it's often described as being a scientific theory. So once it has become what we call well accepted, that there's a general consensus that the hypothesis is a very good explanation for what is being observed, it becomes a scientific theory. Now, the thing that's so cool about scientific theories is that they allow us to make predictions about the outcomes of things that we are yet to actually do. So I know, because, of the operation of gravity, that if I drop an object, it will fall towards the ground. I don't have to drop every single object to know that that is going to happen. It's just going to happen, right? So I can predict how an object is going to behave when I drop it from a height without actually having to do it, right? And so the other nice thing about scientific theories is, in a concise way, they summarize a whole bunch of information, right? They kind of like, I can take a scientific theory and I can generate from that, a summary of how things are going to behave without actually having to look up that information. So that's kind of cool, all right? It's important to realize that scientific theories become improved over time, and that sometimes we have multiple theories describing the same phenomena. So we have different theories of, for example, how we inherit different traits. And they have improved over time. So early theories were perhaps not as good as more modern theories. So we have explanations in biology that are on the basis of biochemistry now that we didn't have back in the day of, say, like Charles Darwin. We just didn't know about things like genes and DNA back then. Now, even though we have some of these older theories that are limited, they can't be used to explain everything, we often continue to use them because within their sort of like limitations, they're very highly effective. So a good example of this are the two theories of gravity. So back, in the 17th century, Isaac Newton formulated a theory of gravity. And then in the early 20th century, Albert Einstein formulated a new improved theory of gravity. Now, Einstein's theory involves some heavy-duty math, and it only is an improvement in a very small sort of like set of scenarios. So most people, for everyday things, everyday purposes, continue to use Isaac Newton's theory of gravity. So when we're planning like moon rockets and stuff, we're generally just working with what Isaac Newton came up with. But when we're studying phenomena like black holes and so forth, then we might have to resort to Albert Einstein's theory. So it's important to realize that a scientific theory is always considered provisional. Now, at any point in time, someone could come up with a new experiment that hadn't been thought of previously. Someone could come up with a new piece of equipment for testing the theory, and it disproves that currently held theory, right? So when we test a theory, there's really only sort of two possible outcomes. One is that the theory gets disproved and we need to improve the theory, or the other is that we gather evidence that supports the theory, right? But we never say that the theory is kind of proven. Okay, so now we're going to do a series of problems where we practice using some of these terms. So it says, in the table below, you will find 3 descriptions of scientists engaging in activities that are part of the scientific method. What are the missing words? So we've got observation, experiment, fact, law, hypothesis, and theory. All right? So let's just kind of list out some of the options here. Observation, experiment, fact, law, hypothesis, and theory. And you might come up with definitions of these in your own words and have them handy on notepaper. So it says, Isaac proposes A. of how a force of gravity controls many forms of motion. He writes down 3 equations that describe how the force of gravity works, and using these questions, he can predict the motions of many planets and also how apples fall from trees. So what he's doing here is he's explaining how gravity controls motion, right? He's explaining why things move the way they do, and he can use it to predict a whole variety of phenomena from apples to planets, right? So this guy here, this has got to be a theory, right? I think a theory is the one that best encapsulates what's in this statement. Now, you could argue that it's a hypothesis because it's just one person and we don't know how well it's been tested. But it does say he can predict the motion of many planets and also how apples fall from trees. So it can predict a wide variety of phenomena correctly. So I think it's well tested. I think theory is definitely the one here. Okay, Galileo decides to test the hypothesis. So he's testing a hypothesis. So how do we test hypotheses? We use observations and experiments to test hypotheses. Galileo decides to test the hypothesis that all objects should accelerate at the same rate under gravity. So he conducts okay? So when you conduct something, we're tossing up between experiment and observation, right? You conduct an experiment and you just make an observation, right? He conducts an experiment. That I think it's going to be experiment. He takes 2 balls, one heavy and one light, and drops them from the top of a tall tower, measuring the time it takes them both to hit the ground. He does this 10 to 12 times. I think this has definitely got to be an experiment. Okay. We've got that one. All right, next. After studying the position of the planets in the night sky for some years, John discovers. So he's making a bunch of observations, right? He's making a whole bunch of observations. John discovers a something which he expresses as an equation that can be used to predict the location of each planet every night. All right. So this is interesting. What this is this is an equation that describes where each of the planets are every night. It doesn't say why they are there. So I think that the best thing that fits in here is it's got to be a law. It's summarizing a large number of observations, right? He observed the night sky for some years. Okay, I think that's great. All right, let's do another one. In the table below, you will find 3 descriptions of scientists engaging in activities that are part of the scientific method. What are the missing words? So remember, we've got observation, experiment, law, hypothesis, and then finally, theory. So you make a bunch of observations, perform some experiments, and you might be able to summarize your results in a law. You formulate a tentative hypothesis to explain why you are seeing what you are seeing. And if that hypothesis is tested again and again and again, and is shown to be correct, it eventually gets promoted to the status of theory. So the first statement, Antoine burns some charcoal and a very small diamond, and makes that the only product of both reactions is a heavy gas. He makes I think it's got to be observation. All right? It's just a record of what he saw. Observation, all right? Okay? So the missing word, observation. Okay. after studying the chemical reactions of many compounds, so we've got a large number of data points here, so this is looking like it could be a law or something else, made of carbon, August discovers something that says carbon always forms 4 chemical bonds to other atoms when it forms a compound. So it's telling you what happens, but it's not saying why. So for that reason, I'm going to say law. So it summarizes a large number of observations, a large number of experiments in a simple statement, but it doesn't tell you why. And that is definitely a law. Okay, Wolfgang develops something about the arrangement of elements in the periodic table based on some ideas about how electrons are arranged in the different atoms of different elements. Using equations, he is able to predict, there you go, the exact arrangement of electrons in many atoms, and from there predict why they are where they are in the periodic table. So what he's able to do here is he's come up with an explanation about why, atoms are the way they are. And this is generally applicable to a wide variety of atoms, So I think that what we've got here is we've got a theory. It has that predictive quality, and it's telling us why things are occurring. And he's tested it against many atoms, right? Many atoms. So I think the best one here is theory. Okay, so we just went through a few key terms associated with the scientific method, and we went through the general process of how the scientific method is applied to solving problems. Hope you found the video helpful, and if you have any trouble with the content, please just reach out to me.